fortunate to have Marija Tomasevic here to tell us about low-D singularities. And so, do it.
Thank you. And thank you so much for inviting me to come here. It's always a pleasure to be back in Berkeley. So I'm going to be talking about low-dimensional singularities. So this is a project that I've been working on with Marija, who is now a postdoc at UCSB. So the rough outline of my talk is the following. Low-D singularities means lower than 4. So we're going to be dealing with 3D black holes and 2D black holes, consequently their singularities. And the one example that I'm going to be focusing on is known as a quantum BTZ black hole, which I'm going to introduce in the beginning. Let me just mention right away that this talk is meant to be a questionable talk. So just feel free to ask questions or to make the discussion. Okay, so first let me motivate why that I'm interested in these things in the first place. So why singularities? Well, singularities in general come in several flavors. We know of time-like singularities, space-like singularities, and non-singularities. Now, usually in physics, we're used to dealing with time-like singularities. These are just some objects in some space that we don't really have enough resolution to see what is it the degrees of freedom that they're made of. So this is something that's familiar, say, from electromagnetism, for instance, where we have the same type of 1 over r behavior at the Coulomb potential. So this will be an example of some sort of time-like singularity. So it's something that we sort of are familiar with. Non-singularities are a little bit different, but let me not even talk about them because one can argue that they always sort of lead to space-like singularities given enough quantum corrections. And we're going to see an instance of that actually in this talk. And so what I'm going to be focusing mostly on is the nature of space-like singularities, which are basically representing some singular moments in time. So it's not something that we're very much used to in physics. As we said, usually we just think about some object that we don't know how to resolve. But space-like singularities are really weird in that sense because I don't even know how to think about a singular moment in time. At least for me, this is a very weird concept. So understanding this weird concept and the nature of these singularities and the resolution is one of the biggest problems in physics, as we know. So this is my motivation for going into this. Okay, so that's why singularities. Now why 3D and 2D singularities? Well, this is because in general, black holes are very difficult to actually describe in dimensions higher than 4, equal and higher than 4. And so the problems that we usually deal with become much more tractable once we go down in the number of dimensions. And this tractability also indicates some sort of hope that we can say something about their resolution and the nature of these, although this is still something that's very complex. And of course, when I say hope, I do mean it through the holographic correspondence, as we're going to see. Okay. So as I mentioned in the outline, the example that I'm going to be focusing on is an example of a 3D black hole, which is known as a BTZ black hole. So I'm pretty sure that it's something that's pretty standard knowledge at this point, but I'm going to introduce it anyway. So the BTZ black hole is a 3-dimensional black hole in an ADS spacetime. It's obtained through a discrete quotient of ADS3. Its metric is pretty simple, where all of these things are very much known things. This is an example of a spinning solution, so we have a J and we have a mass. There's R plus and minus are corresponding with the event horizon and the inner horizon right here. Now, the one thing that I'm interested in here is, again, the singularity structure. So this means that I'm going to be most interested in the causal structure of these particles. So what is the causal structure of this BTZ? So usually, the causal structure of the static BTZ black hole is depicted as some sort of a square Penrose diagram. Is this something that everybody has seen before? BTZ black holes? Okay. So these lines are the horizons, and r equals to 0 is supposed to represent some sort of singularity. However, note that this r equals to 0 surface, even though it looks space-like here, it's actually a null surface. And this is something that actually when I used to give this talk, people were kind of surprised by this statement. So I'm going to just show a little derivation to see why this is.
Why did you try to explain that?
Well, I'm going to explain. So this is the usual way that it's represented, and it's not wrong. But we will see why it's a little bit misleading. So, okay, this is a mixed stock hybrid blackboard. I hope that's fine. Is that fine? Okay. So this is the metric of the BTC black hole with no spin. And in this parameterization, r equals to 1 is the length horizon. And r equals to 0 is supposed to be that's going to be here. Okay, so how do I get, so from here, we don't really see that this is a null surface. So how do I get to see that this is actually null? Well, I do a very simple change of coordinates. I identify this to be some sort of x squared. And then what I obtain is something like this. Of course, now I've done this exercise, so I know what I'm supposed to change. So just by simply changing the coordinates in this very simple manner, I obtain a metric like this one. And now it's very clear why the singularity structure is a null one, aka the r equals to 0 is a null surface. Because here we now see that first of all, phi will play the role of time. It has a minus in front as long as this x is bigger than 1. This one is not playing the role of time. And also we see that this has the same structure as this part here, aka it's in the x and phi directions that this surface is null, not in the t and r directions, which is why here we don't see actually the null structure of this spacetime. So you just do a simple change of coordinates, and you see here this is a null structure, so it's the same as a horizon, right? That's why I said it's the same. And because it's the same as a horizon, you can see that it's actually a null surface, just like the horizon is. Is this clear? Maybe it's very true. Okay. So this also connects to another thing that I wanted to say.
Can you say again? So I'm not able to follow you. So r equals 0 is x equals 1.
Yeah.
And
you see here x equals 1 really leads to this being the generator, this also being the generator, while keeping the dt fine.
yes.
And
So it's the x direction that is timeline, right? And the y direction is space-time.
so
X
the
is less
important,
than 1.
so this is what I want to comment now. As long as x is less than 1, we have that this is actually just a normal space-time direction.
Yeah.
But the moment x approaches 1, so x less than 1 in the BTZ diagram is just here.
Yeah.
The moment you approach 1, okay, this becomes a generator, so you reach the singularity. But you can also go above 1. There's nothing preventing you from going there. And I'm going to explain why. And if you go above 1, then this factor is positive. So this becomes really time, because there's a minus here. And so your time is now periodically identified, and therefore you obtain closed timeline curves beyond this x equals to 1 region. So here everything is pathologically fine, but the moment you go up, you get into the closed timeline curve region.
So what you're trying to convince me of is that x equal to 1
Is a singular.
is a null surface.
Yes.
And
Just like
I'm not.
like
Don't
here.
you need to transform this to some coordinates where it's not null surface?
Well, just I don't need to transform if you remember the horizon structure. So you see that these are the same. X minus 1, r minus 1. And here r equals to 1 is a horizon. So you know that it's a null structure. And because this is the same geometry, it's going to be the same time. You can maybe extract the minus 1 a little bit the same. It's just a very stupid change of coordinates.
So I would have said that the Penrose diagram is square because you can send out two signals from the white hole to left and right boundaries, and then they'll exactly be able to meet.
That is still true.
That's still true, right?
Yeah, that's still true.
So the claim that if this is, the point is that it's also allowed to be null because it's singular at that point, and so.
Well, it's null because you see it in the phi direction. It's not in the t direction. And the Penrose diagram is
sorry, I see.
Yeah.
But keep going.
If you want, another way to see this more on spot is by just literally mapping the solution to something known as the Misner APS3 solution. It's another solution, but there you have it explicitly as known. But I think it just basically boils down to transformation. But okay, so this is the usual, this is the structure depending on the BTC black hole. No. Now I'm switching back to the thing here. I guess that's fine with the light on. Okay. Okay, so here was just a small R-cap, which is the excavation. Okay, so this was the causal structure of the static solution. The rotating solution, however, has the very standard Kerr-Lens causal structure, which is something that we all use. Now, the one other thing that you may notice is these R equals to 0 surfaces are noted as two lines and not as wiggly lines. This is indicating that we don't really have a proper curvature singularity happening in these surfaces. In other words, this R equals to 0 surface is not properly singular, it's only quasi-regular. It's a very proper mathematical definition. And one can really see that it's quasi-regular by taking the R equals to 0 limit, because in the BTZ case, we simply obtain a flat metric, or locally flat. So we obtain a locally flat metric, we just extend through it. And in contrast, we can see that the near singularity for the Schwarzschild black hole is a much more degenerate sort of a structure where you don't get to actually cross. So it has something known as the Kasner form, or the specific Kasner exponential, Kasner coefficient, but you can already see here that both of these are going to degenerate, whereas here it's just flat. So
This is a bit like sort of the Mill solution.
yeah, so the inside is just, the inside is a Misner solution in the BTC case.
Yeah, I just mean like if I replace the R by E in your formula, in the first formula.
Here?
Yeah.
Yeah, you see
that's
it's not-
reminiscent of the Mill.
Yeah.
So you mean like it can be completed or,
Yeah.
and what happens when you do that?
Well, you obtain a space-time beyond this region, just like you would for any other maximal extended solution.
Right, so I guess what I'm confused about is why do you call this only quasi-regular and why don't you actually extend it? I mean, normally if the space-time is extendable, that's what we do.
So, okay, so the reason why I'm not extending it is because this is still a BT solution of people from the beginning of ages, even though the original BT and Z.
It may be from the beginning, I'm just trying to understand, now that you've educated us and told us that this isn't really a singularity,
Yeah.
the way you were explaining it made it sound like it's just not a singularity at all.
Well,
And it's weird that we're not just...
yeah, it's weird,
extending it.
yeah. So I'm going to solve this problem. This is the point of my talk.
So is it?
I'm going to put an actual singularity there, and we're going to see that actual.
Okay.
But if you, sorry, but
Yeah.
what the geometry? If it's if you maximally extend it, it's just ADX, right? It's
If
the
you don't
quotient.
take the quotient of ADS,
Yeah. So you take the quotient, so that's why you try to extend it and just identify it somewhere else.
Yeah,
That's it, right?
that's great, yeah.
Maybe could you say what quasi-regular means?
So quasi-regular means that only a certain set of null geodesics doesn't get to cross this R equals to 0 surface, but everything else does. So for instance, you could find time-like geodesics that are just like very easily crossing from this region across this other into the CTC region. So this-
I thought we were discussing this time-like singularity.
No, sorry, okay, let me make it clear. This diagram here is for the rotating BTZ. And it's very much similar to Kerr. If you were to wiggle these lines, it would literally Kerr in ABS. Or resonance or whatever. Here, this is the static BTZ kind of diagram.
Yes, I understand that, but I don't understand in the various bullet points which of these diagrams they refer to.
This one.
All of them.
Oh. Because
Oh.
in the other case, sorry. Actually, no, sorry, let me take that back. In the other case, I'm pretty sure that R equals to 0 there is also quasi-regular. Okay, yeah, let me take that back. It's not a proper curvature singularity in any case, exactly because it's just a quotient on EPST. The best you could do is some sort of orbital singularity. But it's supposed
Yeah,
to be
so
EPST, so it's
yeah.
not properly singular.
Okay,
Yeah.
but it's like a conical singularity.
Yeah.
Okay.
Yeah.
Okay, thanks.
And the conical singularity is not enough to prevent all observers from crossing. And this is important.
Actually, it's small, it's not in the conical singularity. It's a vertical cut of the diagram, it looks like a sphere.
Okay.
So like
So you mean it's not a
the conical angle is actually.
Yeah, I mean technical, what do you say, its name is orbifold singularity.
Okay, yeah.
You get it from orbifolding. But the intuition is, I think, the same as if you had the conical, aka it's not a very strong symbol. Okay, any more questions? Bobby? Okay, so we see that the r equals to 0 does not have the same form as proper curvature singularities have. And that's really some sort of a problem. So BTC black holes are not only not representing our real-life black holes because they only have 3D and ABS, but also because they have this weird causal structure. And they, very important thing, allow for these closed time-like curves behind their inner horizons. So for the case of the rotating BTZ, this was known before, because this inner horizon is a Cauchy horizon. But we see that even in the static BTZs, r equals to 0 surface acts as a Cauchy horizon, behind which we have closed time curves. Okay.
When you say that causal structure is different, I mean any black hole in our universe presumably has some angular momentum, and so then it has an inner horizon, and you sort of have the same situations rotating BTZ. This seems very special to Schwarzschild, but there's a difference.
I'll come back to that. But yes, you're right. A priori you're right, but we'll see how this actually gets on. Okay, so I gave you the story for the pure gravity solution, but let's see now what happens if we add matter. So there are several ways in which we can add matter. The simplest way is, of course, to follow Durrell and Davis, put some fields on top of a background, backreact, see what is the actual geometry. But there's another way of adding matter, which is sort of easier if you know what you're doing, which is this context of double holography. So for those of you who were at lunch today listening to me, this is going to be very much similar to that discussion. But I'm going to explain it now in a little bit more detail. So the double holography is also known as brain roll holography or Karch-Randall, Mandel-Sundrum, all of these people holography. And it refers to basically just having some sort of a brain embedded in a higher dimensional ADS space. And these are, given that we know of 3 types of asymptotics, these are the 3 types of brains that we can embed in ADS. So this middle region is the highest dimensional ADS spacetime. And then on the left, we have a case with an ADS brain. This ADS brain is also coupled to some sort of a quantum field theory. I put here CFT, but it's actually a CFT with a cutoff. So it's coupled to some sort of a quantum field theory. In this other case, the balloon is actually just representing asymptotically flat spacetime. It's also coupled to some CFT. And the third case is then, of course, the sitter coupled to some matter as well. Okay, so this is one layer of holography. Why is it called double holography? Well, because we can also talk about the CFT duals to these things. So in particular, there's a CFT dual to the actual bulk spacetime. But putting this brain in corresponds to on the CFT side, putting some sort of defect CFTs, which are these codimension 2 defects, indicated as these dots here. So this is just a cartoon, but pretty useful. In the flat case, similarly, you have a defect of this type. And in the sitter, you don't see it here, but actually the defects are going to live in the future and past ahead. Okay, so what is the basic idea of this double holography? Well, I've cut off my ADS bulk with some sort of a brain. And in particular, all of the things that I'm going to be saying right now are going to be explicitly for ADS brains, but the whole logic refers to the entire set of brains. So I'm cutting off my ADS bulk with some sort of a brain. I'm chopping off a part of my ADS cylinder. This corresponds on the CFT side to also cutting off the CFT in the UV. So I'm getting rid of the UV degrees of freedom.
So what's cut off the UV? I thought it was just on.
So in the bulk, it just looks like some sort of a weird boundary that you put in. But you also have to...
Like ADS case, let's go to ADS case, like a left.
Yeah.
Previous page, the left view.
Yeah.
I thought the CFT was originally on the boundary, and you just put the boundary in the CFT space, not UV cutoff. You're not talking about UV. just talk about infrared with the CFT.
Okay, so so in order to obtain this sort of a brain, what you do is basically you start doing the holographic normalization of singularities. You have to put yourself a little bit in the bulk. You define an epsilon surface, what he calls an epsilon.
So
The cutoff?
what CFT are you thinking about? The CFT
General.
on the brand?
On-
Or CFT
on the boundary.
On the boundary.
Yeah, but then you're lowering it down into the bulk, so to say, through
What
holographic.
I have to know now, you just cut in space, and then you put this
Yeah, but
CFT, and then you just close it down.
But this cutoff with the brain, the tension of the brain, is directly correlated with the way that you would think
G
about.
factor.
Sorry.
G factor. the boundary.
That's one way of doing it, but it's also correlated with the fact that you're removing some degrees of freedom of the CFT on the other side. You see what I mean? So that's why I started talking about holographic
Yeah, that's the
normalization.
other way. So that's why I asked if you're putting a CFT on the brand. like,
You
like,
are
put
putting on the brain, yes.
Ah, okay,
yes,
then I
Yeah,
understand.
exactly. Yeah.
Okay,
So that's why I said
saw-
like when I wrote this stuff with the CFTD, but I said QFT because technically this is a CFT with
It's just a plan.
Yeah.
thing.
yeah, it's a point.
But you could do the other one, right? You just put a theory here. You just the BCFT and then brand you just wrap it down.
And that's another way of viewing the whole solution, but it still is the
That's why I'm
fact.
confused.
Yeah, but it still is a fact that on the brain you're going to have the CFT with the cutoff. They are just different ways of obtaining the same thing. So, yeah. So what I wanted to say is you start your holographic normalization, you sort of stop short of setting this epsilon to 0. So you basically have an infinite amount of terms in the brain. But this is what induces this action on the brain to be actually gravitational, dynamical gravity on the brain. And then these high curvature terms you can actually deal with in an appropriate way, which is what I'm going to say to you. So as it's integrating out the unit of the CFT leads to this induced action on the brain. So this is the Skinner's procedure. So the gravity of the brain is dynamical, and the brain theory is some CFT coupled to dynamical gravity. And crucially now, we have some sort of a theory of gravity, which is coupled to quantum matter. So the CFT with the cutoff, so some sort of QFT. And this very complicated theory of the brain is dual to classical dynamics in one dimension hybrid. So kind of like maybe CFT, but now in a hybrid form. So here is what this is. Classical dynamics in the highest dimensional bulk holographically encodes all of these quantum corrections or quantum fields that live on the brain. Is this picture clear? And crucially, it's not only encoding the CFT that we put there, but in fact the metric that we write down for this brain solution is already going to have ingrained quantum corrections from the CFT that lives on the brain. And we're going to see now exactly what is it that I mean by that. This just means, this sentence here basically means that the holography was very smart, and it sort of did the full one loop reformation of the Rowland-Davis many times and engraved all of these corrections into your metric. Right, so this allows us to do things. So, one more thing that I want to just emphasize, which is the duality between these two things, is that we can view these two systems in two different ways. So one way to view this whole system is to view it from the bulk point of view, where we have basically just the Einstein-Hilbert in d+1 dimensions, plus some action for the brain, as viewed from the bulk. And this system together is going to be equivalent to the Einstein-Hilbert action on the brain, plus these quantum fields. So this is the statement that we want to make. So everything that I was writing here, like all of this is basically equal to all of this. Technically there is a plus CFT over here. Clear? Okay. So let me now go to an example, which is actually going to be useful for me. So remember, why am I using this double holography? Maybe you forgot it by now, but the point is for me to look at the BTZ black hole and add some sort of a matter to it. Okay, so looking at the BTZ black hole with matter means that my brain is going to be three-dimensional. So I'm going to put myself in a setup where I have an ADS4 bulk metric. And there's a very specific metric called the ADS-C metric, which is given in this term, in this way. And it's a very useful metric to see, to deal with. Technically, it describes accelerating black holes that are accelerating away from each other. But one can also see that they're very easily usable in this double holography sense. And they're easily usable because we can slice it along one of these directions, this x equals to 0. And if we do it, we simply obtain a metric of the brane, which is given by this trivial formula. And you see here that this h of r, so this g of x doesn't appear anywhere, so you just forget about it. We see that this h of r, if I was to set this term here to 0, we just reduce down to btz. Is that clear? This kappa is just setting the overall topology. And so this what's it called? This term, mu times L, is what is actually new about this metric. So these are the quantum corrections that I'm actually ingraining in my metric. And these are two separate parameters, mu and L. Mu is something that is set by bulk regularity, and it says basically the stress tensor or the CFT that lives in the brain. And this is why we call it a quantum correction. It comes from the CFT that's on the brain. So mu here is proportional to mu. And this L parameter is something that determines the tension of the brain. And it's a parameter of my fear in general, not just of the solution. And this parameter L basically determines what is the distance between my brain and my would-be boundary. So for very small L, I'm very close to the boundary, I can suppress all the high curvature terms.
Sorry, maybe this is a little bit detailed, but if I remember correctly, for C metric, it's like this RT plane is actually a compact space if you incrementize it. But for BTZ, like you should have RT plane to be like not compact, right?
Okay. If I Euclideanize it, I have some
Yeah,
sort
like
of-
the time is periodic, and R is, if I remember correctly, R is within a range, a finite range.
Okay. R is in the finite range.
Yeah, but
Oh, okay, so, yeah. Okay. I don't know if what you mean is this particular form of the metric that I was showing. There's many forms of the symmetric. So, if
Okay.
R is what I think is the thing that I just wrote down here, it's a bit weird to think about its range because R equals infinity is actually one of the lines inside the loop. So it's somewhere here.
okay.
And it's actually here, when you hit the boundary, R is here proportional to final, minus L. I think that's
okay.
So it looks like it's finite, so I don't know if this is what you have in mind.
Okay.
But you see that we never go in this direction because for us, we're always at this x equals to 0, which also gets rid of this conformal factor, which is basically the reason why this infinity here is at this weird point.
Okay.
Yeah, so I don't know if that answers your question, probably not, but maybe
Yeah,
we
well,
can-
I think
look at something
like
else later.
it's some specific form of C metric maybe. Might be a little bit detailed. Thank you.
Okay, yeah, we can sit down and actually look at it. Okay, so I'm giving you now a BTC metric which has some matter, it's already ingrained in it. Okay, so who cares? Well, I cared because this new term that I was adding, so remember my new metric is now something like this. My GTD factor. And this new term that I put here goes as 1 over R, and it's exactly the reason why I'm able to have a divergent Kretschmann scalar in this geometry now. So, by putting in matter, by back reacting on the geometry, I was able to obtain an actual space of singularity in my 3D plane. Is this clear? So this is very nice because this now quantum correction actually then reinforced what is known as a chronological protection principle, or sometimes known as a cosmic censorship conjecture, where before putting in matter, we were able to cross this null surface R equals to 0, but now we're actually forbidden of doing so. So we see that first, not only did the null surface now actually bend down to being a proper space-like surface, but also it became impossible.
So when you say the Penrose diagram is no longer a square, you mean that you can't send two signals out from one?
No. Now it's a proper square.
Oh,
Even
sorry,
if-
it says no longer a square.
So, okay, yeah. No longer a square as in, it's as a Schwarzschild black hole.
Yes, so it does bend
Yeah,
down.
sorry.
So
Square, it's not a square, it has an actual proper singularity, yeah. And it's very much the same with Schwarzschild ideas. And we know that because of the argument that I'm going to show you later, but you can actually calculate it. It has the same cancer form. Okay, so if you care about real life, it's much more attractive. So this fact that some curvature singularity actually prevented us from crossing some sort of pathological side is a part of a bigger story. And it's just one instance of the strong cosmic censorship conjecture that I mentioned previously, which basically states that all Cauchy horizons are going to be singular. Cauchy horizons indicate generally regions of spacetime beyond which we can no longer use our equations of motion to predict what happens in this region. And we see that by putting in quantum effects, these Cauchy horizons become not only weird to cause, but actually impossible, because there's this curvature singularity form. So this strong cosmic censorship conjecture is something that has been conjectured by Penrose in the 70s to prevent all sorts of weird things from happening if one actually managed to cross it. So experiencing time machines would be one of them, because remember there are CPCs behind. But also we would be allowed to see the time-like singularity in case of Kerr. So if you remember the Kerr case, like we have something like this. So I found a person here, I will be able to go through this inner horizon, which is a Cauchy horizon. And so the time-like singularity would be in my past light code, so I'll be actually able to see it. And then if I'm able to cross it all the way, eventually one can imagine going to another universe with another CFT and telling all of my friends about it, about all the quantum gravity that I saw. But Penrose said no, and this is exactly what we're seeing. Now this strong cosmic censorship conjecture was formulated in the 70s, so there's been 50 years of work on it. But in fact, it's been only, I guess 5 years ago, when people realized that putting quantum fields in our black holes is what leads to some sort of a universal protection from crossing this sort of inner horizon. So this was done by Collins, Wald, and Tan for the first time, as far as I remember, but there's been many follow-ups, also by Collins and other people. And so what they've shown is that if I just take a black hole and I put some quantum fields on top of it, a la Davis, I can calculate what is my stress tensor in some sort of a particular state, but it doesn't really matter which one. And what I find is that my stress tensor has a very universal form, which Arvin might disagree with. But at least there's one term that is properly universal, and there is this one, that is this one, which goes as 1 over v squared. So this is a term that comes from the quantum correction, and we see that because this constant is h bar dependent. These subleading terms can also be singular, but they don't have to be. They come from the classical contribution of the stress tensor. And it's very important.
Remind me what you're wanting to say about this, just for comparison.
So maybe not now, I'll tell you.
But in summary, were you wanting a larger divergence?
Maybe a larger divergence.
So Arvin would say,
I can't summarize it.
Arvin might say that, well, perhaps this is not a leading term. Perhaps there are other terms before this one that are more divergent, but for the purposes of what I want to show, all that I care about is that it's divergent in some sense. And it has to be divergent enough, and this is where the square part here is actually important. So these subleading terms have some form like 1 over v to 2 kappa plus minus kappa minus, for instance. I don't remember the exact formula. Where these kappas are associated surface gravities of the inner horizon and the outer horizon. So depending on the ratio between these two temperatures, you can see that this 2 can go to 1 or 0 or some smaller number than 2. And if it's a smaller divergence, aka weaker ones, it's like 1 over v, for instance, then math people have shown that this is not enough to prevent all geodesics from crossing the surface. So in order to have a proper singularity at this horizon, you really need 1 over v squared. In order to induce the stress tensor divergence, that will be enough to show that the Kretschmann also diverges there.
Sorry, is this like related to the space-time dimension, or is it universal to all the dimensions?
So this is our
Okay.
this v squared part for sure will appear in all dimensions, but the fact or the question of whether or not there might be more divergent
Hasn't
terms
been shown.
is
It's exposed up. Maybe it's explained.
Yeah.
You don't expect it to suddenly become better in higher dimensions, but
yeah,
their calculation is
it's a 4D.
numerical one for it.
Yeah, it's a 4D calculation. One can show it in 2D explicitly that this is the leading term, and I would agree with that.
But 2D, the dimensional analysis.
Yeah, by dimensional analysis, basically. Yeah, okay, and I'll show you what happens in 3D.
And you were saying that like this v square divergence is enough to prevent the geodesic goals.
Yeah.
Okay.
So if you want a good criteria, you just have to make sure that the C is not 0, basically. As long as your C is not 0, you're fine with your inner horizon. That's why I said like wait a little bit with the curved black hole, because curved black hole does have an inner horizon, which is a priori very smooth. But once you put quantum fields on top of it, they will lead to this kind of a divergence, and they will make this inner horizon actually not smooth. They will make it into an actual singular place. Now, this is all a very nice story that works for many black holes, but there exists a very notable outlier to this picture, which is the rotating BTZ solution. So before I was talking about the static one, but it's actually the rotating solution which is okay. Interesting. And you can see this in this very horrible expression, which is the only reason why I'm using slides here. So this is a bunch of things that I've extracted from Hollandswald and Son. But as you can see, all of these papers from 2019 basically said all the same thing, which is that the BTZ inner horizon for the rotating case, it sucks, and it's very passable. So what these people have done here is to show that, well, we want to calculate that coefficient C that goes with 1 over v squared. In order to calculate C, it basically boils down to calculating this n. This n is given in terms of a bunch of things, and a bunch of these things are just basically products of gamma functions. And you can see for the very specific A, B, and C, which are all just parameters of the rotating BTZ solution, they just all magically product away to 0. So this is some magical outlier that's only valid for rotating BTZ, basically because all of these guys conspire to give you a 0.
So let me know the basic thing, like, I know this is a basic question. If you put a matter, or if you just introduce a matter in the theory, what was the physics leading to this energy momentum tensor? It's just...
so you calculate the stress tensor of this matter.
In what kind of state? You told me a lot, but it's just what?
You can calculate it in the Hartle-Walking state if you want.
Hartle-Walking states.
But if you noticed before, that maybe is a very important point. This depends on the state, but you see that the whole expression is state independent. So this C is just a quantum correction, but it doesn't depend on the parameters of the solution. That's why it's a universal response on the field.
It may depend on the sector. I think in that paper, technically, they do it for the en route state, actually.
Yeah,
in
it's
the
on the other side, yeah.
the Sitter Ricer notion, they have a very specific goal in mind. And in the en route state, any state in that sector has this property. So I can actually operate.
The unruled walking is the same as one.
But the question is whether there is no state which may be zero, or it may not be here.
Not that sector. Not
in that sector, yes. But it's,
or Hawking is bad, en route is bad.
so okay, some reasonable state, you take the reasonable state from some other, whatever reasonable physics consideration, then it's over.
Yeah.
Yeah. I mean, you have to just make sure that it obeys the Howard line property. That's all.
Sorry, when you say C is state independent, do you mean it's independent of the parameters of the black hole, or independent completely of the state? It's just both. Okay.
No,
It's independent. No, it's is there any? I mean, no, I think there's no dependence on like
the hole in the wall
Yeah.
thing, it does depend on like the ratio of the radii of the black hole and the cosmic horizon and stuff. For
The
example,
1/v squared.
the C, the coefficient C, is not state dependent, but it depends on in the sector. Yeah, there is a dependence, but it's,
On the temperatures?
yeah.
I don't remember. Okay, we can look at what, it might,
It depends on the kind of quadratic states.
Yeah, depending on like in which fields you act on, but it depends on some fields of the background, I think. We can discuss it.
we can take a look, but I know that they were very explicit by saying like, there is no dependence on anything related specifically to this type of black hole, because for me, it was sort of an intuition that you're going very close to this.
C has to be dimensionful, right? In that.
Okay, in that
4D.
sense, yeah.
So it's dimensional, it has to depend on some.
Okay, that's right.
So it
That's
depends
right.
on like a radius of the horizon.
Other than
Okay, yeah, but it's not a, okay,
Yeah,
I see.
it's not dimensional because it's secure
Yeah,
from
no.
their background.
No, yeah, okay, sorry, you might be right, but it's not a number that would actually ever go to zero.
No.
Yeah, so in that sense, it's only this C that can actually go to zero and make this. I should be more precise, that's right.
So they don't make, sorry, it's just, they don't argue that it doesn't go to zero. Actually, there's some people which have computed this for all possible things, and there is some specific values where C actually goes to zero.
Yeah, but it's very non-generic,
Yeah,
when they
very
check it,
non-generic.
but it's the C one that is actually important, not the other thing.
Yeah.
For instance, you would see the same thing if you were studying the nearest one.
Yeah.
Okay, so this looks kind of bad because it looks like there's a product of gamma functions preventing us from, well, not preventing us, but allowing us to see quantum gravity. So let's see what happens if I add non-quantum corrections to my rotating BTZ black hole in the same type that I was adding into my brains before. So as for the static case, I can just simply obtain the quantum version of the rotating solution by taking rotating ADS-C metric, which is also a thing that exists. And you see that it's a very simple modification. And this mu L over R again was 0, you would obtain back just a rotating BTZ solution. So it's the same type of correction I want. So it turns out, actually, just simply adding the quantum corrections by inducing them from this holographic CFT is absolutely not enough to make this stress tensor diverge at the interface. So we've done the calculation, you can check yourself. In fact, this C again goes to 0, so to say, colloquially, at this interface.
Sorry, I got
It's not the C goes to 0, it's just that the stress tensor is very smooth in this case.
I got a bit lost in the J equals 0 case, that stress tensor did diverge.
So in the J equals to 0 case, you never have to calculate the stress tensor because you have a singularity already in the metric. So here, what we want to do is start with a smooth-looking solution, which has a smooth inner horizon. And then on top of it, put a quantum field.
I understand, yeah.
So the logic is like this. If I take rotating black hole, rotating BTZ, and I put one quantum field on top of it, like Hollands-Walden's did, I get that I can still traverse through. If I now take the rotating BTZ solution and I put many fields on top of it, like I do here technically, because it's a large N CFT that's back reacting on my metric, so this mu L over R is a large N CFT back reaction, I still get to cross the horizon. But now, the reason why I showed you all of these other guys is that you can sort of imagine that if I was to take this quantum rotating BTZ solution and put yet another scalar on top of it, kind of like what these guys did, then the ratios of these gamma functions are going to actually change, and you can imagine how they're going to lead to something non-zero. And this is actually what happens. So this is something that we did and checked, and you need basically n plus 1 fields, so to say, in order to see that this back reaction on the inner horizon is strong enough to actually prevent you from crossing it. So it's a very special feature of the BTZ solution, but the physical way of understanding this calculation is to say that, well, just doing the one-loop calculation is not enough. One really has to go further in loops, like quite further in loops, in order to see that there is an effect preventing you from crossing. But it's still the same type of an effect. It's still quantum physics preventing you from crossing.
Sorry, what?
Yeah.
You said when j equals to 0,
Yeah.
there's already a singularity.
Yeah.
But didn't you say that that's like not too bad singularity?
In the BTZ, so maybe I can just, okay. I'm gonna put in an extra slide now. So this is BTZ, and this is quantum BTZ. And this is J equals to 0, and this is J not equal to 0. Okay? I'm gonna.
Sorry.
Thank you. Okay. So this one has a smooth inner horizon, and this one has a smooth inner horizon. If I add quantum corrections a la brane world construction, this one becomes singular, but this one is still smooth. So here I need extra scalar field to make the divergence.
I don't quite understand why that extra scalar field couldn't be incorporated in the CFT that's already existent.
That's what we
Wouldn't
expect.
wouldn't that just change mu, but wouldn't actually change the expectation value of the stress tensor?
Well, you're coupling a different field on top of this. You're not coupling a CFT of any kind, you're coupling now some scalar.
Let's say I do a free scalar, which I think is what those people
This is
did,
exactly
right?
what it is, yeah.
This here is here.
Yeah, there's another CFT.
That's,
Sorry, isn't it one way to say it is that it is in one over
yeah,
n correction.
it's right
with
that, yeah,
criminal.
exactly, yeah.
At leading order in 1
So,
over
yeah.
n, it's absent, but with 1 over n. First order in 1 over n.
Yeah, exactly. So this is why I say like it's 1 over, sorry, it's you try to add quantum corrections, but you see that it's not enough, you have to go further in loops in order to see that something actually happens. Another way of saying that is that, well, in the bulk is where I have all these quantum fields, but here they're seen as 1 over n and not h bar, so to say, corrections. So this 1 over n is exactly what Armin was saying now. On the brain, by adding this extra, by including this extra degree of freedom, I'm kind of like computing the extra loop on top of my already quantum solution. I see you're not very happy with that.
Suppose that you add not one field, you add another n free scalars.
Yeah.
You would obtain like CFT whose central charge grows by n. And the constant c would probably also scale with n, right? Because that constant is just, we can define the stress tensor as the sum of all stress tensors in each theories. We have n theories, so it's proportional to n. I don't understand why it's a one loop effect that will be suppressed in n from this perspective. I don't understand why it's a higher loop effect. That's why I understand the calculation that you take this metric and you do the same thing that Wald and company did,
Well, it's
and
one
you find
loop.
a non-zero C.
So it's one loop in the sense that you can sort of think of this quantum BTZ black hole as sort of just like some space-time. You obtain that in the larger limit, it's just some space-time. And then you put a quantum field on top of it. In the usual Berkeley-Davis sense, you would say, well, this is a non-neutral vector. So this is the sense in which I make it here. So we interpret this mu L as having come holographically from the rest of the CFD that exists in the brain. But calculation-wise, it's the same as Berkeley.
Okay. Somehow everything seems to be needed, right? If you just C is 0, and if you just put the C equals 0, a lot of C equals 0, then still C equals 0. Going to holography, you're just going to interaction, about reaction, and everything. That's needed, but that itself is also not enough.
I see.
And then you have to go to the next order in 1 over n with the interaction included. So I think that seems to be the only interpretation.
Good. So you have already in your, I guess the first paper, your you've already argued the 1 over n correction?
Yeah, I'm going to do this now.
I see. Is there any, my question is there any advantage in like putting a free scalar theory on this background as opposed to just a natural 1 over n correction of the brainwork theory? Because the brainwork theory presumably doesn't have a free scalar.
I don't know what the brainwork theory know that there is some CFD, but it's like a whole thing. So this scalar calculation is really just a sort of a probe calculation. You would just want to see what happens if I put some field, then you expect everything to be really scalar. The correct real-world sentence would be, well, I include all my graviton fluctuations, and they are going to actually do this, regardless of the fact, do I have some quantum fields outside or not. So it's just a sort of show principle kind of calculation. So if you were to do the 1/n exact calculation, it would for sure.
You have already argued with it. You're saying this is indirect using the bulk. That's
Yeah.
enough.
Yeah, lots of people, George Santos complained.
Oh, okay.
He was like, no, this is never going to work. And then we're like, okay, let us do it actually properly.
So, just
Yeah.
to make sure I understand. So, like, is the statement that you're making that, like, strong cosmic censorship is upheld regardless of the number of fields if you go to order 1/n squared, I guess, but here, to specifically do that, rather than actually computing the loop, like the actual loop correction, you're just adding a second scalar field? And
Well, as I was explaining, the way that you do the calculation, this new calculation, by adding this one extra scalar, is the same as in Berlin-Davis. And when I say Berlin-Davis, I just mean quantum field theory on a curved spacetime. So you take some metric, you declare it, this is a spacetime, which it is, and then you put some quantum field on top of which properly quantize and do everything as one should. So that's one thing, and there you would say that this is really a one loop correction to your geometry. This holography way of thinking is kind of like a different expansion. It's not a one loop expansion, it's like a large N expansion. So all your diagrams are rearranged in a different way. So it's a little bit different how to think about it. But yeah, the language is that because it's a large N thing, that's why you think about it as 1/n. But in a technical sense, you're doing this one loop on top of this curved spacetime which you fixed. I hope that was clear. If it's not, I have 5 minutes. Okay. This is not going to work. Okay. So as I said, like we can do the calculation explicitly. This is the paper. This is what we've done. But we can also argue that this is going to be true. And so let me just argue real quick because this is the talk that I gave 4 years ago that you definitely don't remember. So this is just a cartoon version of what I was drawing before. So this blob is just a black hole. And if I was to move this brain quite on the towards the center of this bulk, aka I was going towards the tensionless limit, if I really just let myself be in the tensionless limit, what I would obtain in the bulk is Kerr ADS4. If I'm slightly away from the tensionless limit, my bulk black hole is not Kerr ADS4, but it's sort of a squashed Kerr ADS4. But it doesn't really matter. Now, you see that this brain is sort of just cutting through this black hole. And this is exactly how we obtained our black hole in the brain. We sort of took the 4D black hole and we cut through it with the brain. So the brain black hole actually shares the interior structure with the black hole that's in the bulk. Yeah, okay, so this is just like moving it towards the boundary, it's just you get a more easy-like structure. So because these two black holes share the interior, whatever would happen for the inner horizon of the Kerr ADS4 black hole is expected to happen for this 3-dimensional black hole. And this is what we argued previously, that, well, we know that Kerr ADS4 is going to obey the strong quantum censorship, so this implies that the rotating quantum BTZ solution is going to obey cosmic censorship as well, because they share the same interior structure. And in fact, in some sense, we have shown this, because in the Kerr case, we've technically added some quantum fields. They do allow us to do some other quantum fields in this brain, and this is what we computed and showed that this is true.
So, can you explain that part with, like when you say like this, it seems unnecessary to add in quantum field or anything, right? It's just true.
Yeah, that's what I would have thought. That's why I wrote the paper. But then again, people complain.
That's what I don't understand. It's in the, if you can have shown that Kerr ADS4's horizon is singular, which has not been shown, but I think I believe. Then it's like a complete, seems like a complete argument.
Yeah. You have to believe double holography.
Oh.
That's
sure, but
perhaps
that's a different issue from whether you have to add more field.
No, sorry. Current ADS4 on its own does not obey cosmic censorship. It has a smooth horizon. You have to add extra stuff on top of it in order to see. Just like for the Holland's Wald and Sand, what they did was some sort of a version of taking a smooth inner horizon and then putting it on top of it. It was a resonance considered for other reasons, but one can argue the same kind of calculation for current ADS4. Hasn't been shown explicitly, but it's widely believed because it's pretty much very similar to whatever happens.
But what you were actually doing was putting a scalar field on the brain
Yeah.
rather than putting a scalar field on top, right? So if you put a
Yeah, so-
scalar field in the doubly holographic bulk, then it would be co-ADS4 and the singularity would show up for the reason it presumably does that.
Yeah, that's the argument, that's this
Yeah,
argument.
that's the-
Yeah,
So
so,
it's
so they're not the same argument because you're adding
Yeah.
different scalar extra degrees of freedom.
Yeah, you always have to add extra degrees of freedom.
Yeah, but there's different places you can add.
Well,
I mean,
if
they're
you
like-
add it, technically, if you were to add it in the current ADS4 case, via double holography, you should also add something on the brain.
Yeah, but it's not just adding a scalar field in the brain.
It will be some
I mean, there
different.
will be some scalar field mode, but
Yeah, it will be
it's
some
not the same
different.
thing.
It will be a different matter.
It's just a natural one-over-n correction.
Yeah, exactly. It's exactly the
Yeah,
same.
you don't have to add explicitly a matter. It's just that same theory, one over n correct.
Sorry, but it,
Kind of like, think about ADS CFT in general. If you just have ADS bulk and you put some quantum fields in it, on the boundary side, you say, well, I have a 1 over corrected, whatever, observable data.
yeah.
So this is the same thing.
Yeah,
It's
but
just
I'm
you-
saying, okay, you have to take in the doubly holographic bulk scalar fields into account, right? And that will be corresponding things in the brain. But you know, there is a difference. I'm saying putting scalar fields localized on the brain is not the same thing as there being a scalar field in doubly holographic bulk. They're somewhat related, but they're not the same.
But I do is enough to.
I think, yeah, it's enough to show this. We just want to do a proper calculation. Okay.
Sorry, just to clarify. So, like you mentioned that the quantum BTZ, quantum rotating BTZ is having a smooth inner horizon. Is that consistent with a empty curve ADS4 is having a smooth inner horizon?
Yes.
And then
Yes.
in the curve ADS4, if you add in matter, and it will have a like non-smooth singular inner horizon, and it will translate to the quantum BTZ, rotating quantum BTZ, so that it also has some similar.
That's the time.
Okay.
Yeah, good. Okay, any more questions? Well, I'm done with the talk, time-wise, but not content-wise. I don't know if, well, maybe I can just.
You can keep going a little bit. You have other questions.
Okay. I was gonna switch things. Okay, yeah, this is like a general sentence. Well, we see that quantum effects in one way or the other, maybe it depends on how many of them you have to add, but it seems like they are enough to preserve sort of consistency. Alright. I was gonna switch gears now, and I'm gonna switch them very fast. And then we can talk about it if you guys are interested. So, that was all the case for the 3D black hole, and I would say that by showing that the strong cosmic censorship holds for the rotating BTZ, we more or less kind of close the chapter on this story because, okay, one should show explicitly that it should work for Curry ADS4 and higher dimensions, but these are all expected to be true in general. So we sort of close the door on one side, and this student discussion that I want to now start is sort of opening the doors on the other. So for this reason, let's go back to the static case and look at the static BTZ black hole. So I can just take the BTZ black hole and reduce the solution down to ADS2 and talk about some sort of a JT gravity, right? So my BTZ black hole had this metric which was minus r squared minus 1, the r squared over r squared minus 1. That factor already is ADS2, and then I just have some sort of a circle. So I can reduce the BTZ to ADS2, and now I can ask, well, now I have a quantum BTZ. Can I reduce it down to ADS2 as well? And the answer is, well, obviously yes. One would obtain a modified quantum JT, and here I use the word quantum as coming from the quantum BTZ, not as this JT is actually quantumly interesting. But it's just some sort of a modified JT gravity, or in other words, it's some other dilative gravity with some other dilative potential. Now the interesting part is that this quantum JT, or this modified JT, now incorporates space curvature singularities. Because remember, this is a GPT factor that I was talking about, this incorporates space-like singularities. If you were to calculate a Riemann, it would go to infinity, for r equals to 0. So now I have a Dilaton gravity which has space-like singularities. And I can map this to a specific Dilaton potential by just using a very simple thing here. I just read off from my on-shell solution what is my Dilaton potential. And the units here, not the units, but the conventions here are a little bit weird. Usually people put a plus here, so just think of this as plus, plus, minus. So let me
Maria, are you claiming before we do the quantum correction and the whole of BTZ dimensionally reduces to a JT solution?
No, spherical sector.
Sorry?
Spherical sector, you just strip off the circle and you just
Yeah.
have the ADS2 solution.
Yeah, okay, but it's not JT, right? Because the Dilaton
It's
is
classical JT,
size.
if you will. If you start
I mean, okay, if by JT you just mean ADS2, then.
Well,
Right, but normally when we say something reduces to JT, then we also want the Dilaton to reduce
yeah,
to
I
the
agree with that. Yeah,
size of the
but this is this is why I said it's class. It's
But even
ADS2.
classically that would be true, right?
But it's traditional JT without the extremal entropy term. That's the only difference. You get phi of r plus 2 and stuff.
But I don't think
It does. The Dilaton is literally just the
size of
GRR term. Yeah.
is that really right? If just standard BTZ not near the horizon?
Static BTZ. Yeah.
Okay.
Not
J equals 0.
J equals 0. Yeah.
Yeah.
Okay.
There's a problem when you think about it if you want to do quantum shorting, if you will.
Okay.
Because then you have to take into account all the KK modes that would come.
Yeah.
Whereas in the rotating case, those are kind of suppressed. So that's why you cannot talk about the quantum shorting because it entangles with these other modes, but we can still talk about the classical. Which is as far as I will go today. Okay, so we have this modified Dilaton potential, and you can ignore that A there. This is obtained from the general rotating BTZ solution, but let me put to 0 because that's connected to the span.
So R is not equal to the constant.
R is not equal to a constant.
R is equal to U prime of phi, right? So it's not ADS2? What is it?
No, it's not dangerous.
It's not
This, so if you put mu to 0 and A to 0, this is just the standard ADS2.
Yeah.
So this makes it different.
I see.
And you see actually,
It's just what's the at what point I guess should we stop calling it JT?
immediately. I mean, quantum JT is because it comes from quantum BTZ,
Yeah.
but it's just some Dilaton. There's some 2D gravity specific Dilaton potential. And we see that this Dilaton potential is actually kind of interesting because it's singular at phi equals to 0, which is exactly mapped to the r equals to 0 singularity on my metric side. So phi is equal to r in this model. Okay. I was gonna now tell you how I can obtain this action from a 3D and a higher D perspective, not just reading off the solution from the 2D. But that's gonna take me a while, so let me just say it in words. We can add in 3D some sort of a classical conformal scalar and reduce down to the same solution. But then I don't get to actually choose these parameters if they're gonna be connected in this way. One could say, well, why did you do this classical thing in the first place? You could just do the quantum BTZ thing that you started off. But we don't really know what is the exact CFT on this brain, so I don't really know what action to put there. However, I can dualize it by using that relationship that I showed early in the beginning of this arc. I4 plus I brain is equal to I3 plus I CFT. Just express this whole side of the story by the 4D side. Or in other words, I can take the 4D ADS symmetric and try to dimensionally reduce down that solution to 2D. But that seems to be actually not doable because the action is not reducible. It has some sort of a, what's it called? The warp factor, this is the warp factor, that makes it impossible to reduce down to 2D from the 4D perspective. It's this a very similar thing happens for curve lighthouse, for instance, or whenever you have a warp ADS. Okay, I'm skipping all of these details just to get to the point. The point is that regardless of the way that we actually obtain this action, we could have just like closed our eyes and said like, well, here's an action that does incorporate some singularity, doesn't matter where it came from. It has a physically well-motivated, so to say, potential. So can we actually use it to study space-like singularities through the lens of dilaton gravities, or in other words, by mapping it to some sort of a matrix integral? And one can hope to obtain some sort of a matrix dual to this, and thereby shed the light on its resolution. So let me just mention here, so I haven't done this yet, there is some progress that we can discuss later on. But let me maybe mention one fact why I think this is more maybe useful than just general holography. Because what is the point here? Okay, I have some black hole in 2D, it has some space-like singularity, and I want to find its dual, but why bother going to 2D? I already have the story in higher D, right? So I have a holographic CFT dual to a black hole which has a space-like singularity. Why would I do that? Well, it's known that in higher dimensional CFTs, we don't really know how to go beyond horizon and extract information about the singularity in some meaningful way. But here, whatever the matrix model, the matrix integral dual of this dilaton gravity is going to be, it's going to be defined by the fact that we have a space-like singularity. So this potential U5 given by this JT part, Q0, plus something that goes as 1 over pi squared. And as I said, phi going to 0 is the singularity. So this defines my matrix integral and directly incorporates the fact that I have a singularity. So that's why I think it's a little bit more interesting to think about this from the matrix side, because you're going to be defining a matrix model directly connected to a singularity. Unfortunately, we haven't done anything on this yet, so this is the stay tuned part. Okay. So I skipped a lot of details in the end, but you can ask me about it if you are interested. Let me just summarize right now. So what have we done? Well, we have reminded ourselves about the BTZ black hole. We've seen that adding matter to the BTZ black hole gives us new possibilities for studying properties of these things, and we've seen that quantum corrections save strong cosmic censorship. And that going to 2D actually makes some sense if we want to talk about resolving the nature of the space-like singularity from some sort of unique perspective. So, thank you very much for your attention. Sorry for going over time. Well, I'll also be here so you can ask me.
No one has a question. I'm still unhappy about this claim that J equals 0 only BTD has a smooth horizon. So from what I understood, you're saying it's like Schwarzschild where the bit as you're approaching what we would normally call singularity is like the white hole section of Schwarzschild where you're doing some identification of T and T plus 2 pi of Schwarzschild, right? Because pi is periodic. And that's the thing that would
You
become...
mean this x coordinate that I was using?
No, yeah, well you have the x coordinate. I thought x was playing the role of like R.
Yeah.
Schwarzschild, and
when
phi is playing the coordinate T,
Yeah.
right? It's the one that's space-like, and then we'll go to time-like.
Yeah.
But if we take Schwarzschild and we periodically identify Schwarzschild time, I wouldn't have said that is like the different patches of Schwarzschild are like connected together in any reasonable way. Like if anything, maybe the black hole region is connected to the white hole region or something, but certainly...
I don't know why I keep mentioning white hole. This is just the maximal extension of
the point, okay, there's a region
so
where...
you mean the future white hole?
So, forget about what...
Yeah.
We're inside the black hole, right?
Yeah.
We're in some region, phi is space-like, x is time-like, okay? And then we're going to switch to phi being time-like and x being space-like, but we periodically identified phi before that. So that feels almost the same to me as you're considering the white hole patch of Schwarzschild, T is space-like, R is time-like, and then you're periodically identifying T, that's fine in the white hole region. You can also, of course, do it in the exterior region, you get close time-like curves.
Well, how would you
but
get...
they're not connected together.
But you think...
It's like the double cone.
Yeah, it's the double cone. But in the double cone, you wouldn't simultaneously talk about the white hole and the black hole, right?
I mean, maybe that's...
Well,
in the complex plane, you can...
Yeah, I don't know, in this, you have to be, sometimes you do want to talk about them being connected I don't know how to think about it here.
But are you thinking like, well, I have a Schwarzschild solution like this, and here is my white hole, and then I can go up?
You're claiming that the BTD looks like this, where this direction is phi, and this direction is x, and what we normally call the singularity is x goes to 1, but at least if phi wasn't compactified, then fine, I totally believe, you have some other region beyond the horizon, you presumably also have a fourth region up here, right? What we call them 1, 2, 3, 4. It's not the standard ordering for whatever. So we're not in the swatch chart, right? 1 is the one we have, and then if there was no compactification, I believe there's 2, 3, and 4. But now we're identifying, we really only have like a wedge of this, right? We glued here to here. So now we have that wedge, and that wedge contracts to a point up here. And then I don't see why we should also say, therefore there also exists this wedge with this periodically identified with here, and same with this, and same with this. Like maybe I believe in this one, but I don't think I believe in these two. They seem like pretty different. And yeah, there really is some sort of singularity here where there's only one.
Yeah, it's a wonderful singularity.
Yeah, fine.
Yeah.
But, okay.
But you can cross to the other.
In that diagram, you called it smooth.
Well, sorry, yeah, sorry. It's smooth as in there exist geodesics that can still cross. So for me, that's smooth. Even though it's quasi-regular is the actual name for it, but...
Jeff, you agree that there are geodesics crossing from 1 to 4, right?
Yeah.
A geodesics crossing from 1 to 4, that seems fine.
If you could find just
Like-
one geodesic, that would already be a problem.
Okay, you could also, in the uncompactified thing, you'd have geodesics that go into 2 or 3, right, formally.
Yeah.
But these are going round and round phi infinitely many times, and they're infinitely fast. And I don't know, it's just not at all obvious to me that, like...
But I don't think she's claiming that region 2 and 3 exist.
I thought you were, because you said they were close time-like curves.
But they're in 4.
Wait, where are they in 4?
They're going to be above, when phi now starts being pi.
I thought this was more like going from 1 to 3.
Still space.
It's like going from 1 to 3, where there's space like difference too.
Oh, I
Yeah.
2 and 3 is where phi will be time.
Yeah.
Oh, okay. But then, yeah.
I mean, you can get that. I understand the argument that formally, in the uncompactified solution, you knew this, and then, okay, you go infinitely fast throughout. I don't know.
Is there a real problem? It seems like, the geodesics seem like they're fine. As long as you talk about what happens at the tip. To regulate it somehow.
So, I mean, the name of the game is that geometry may be weird or not above this region, but as long as you can find single geodesics that can cross, that's already a problem.
Is it important
It's
for you
not
that
obvious to
they
me.
is it important for you that they cross to a pure time-like curve region?
Well, important for me to cross. I don't know if it's important, but it's what happens. As I said, you can also map it to a proper solution.
I would say there's no singular. Look, if the metric stays non-degenerate, you can find some coordinates where everything stays regular, then clearly things can pass through it and nothing breaks down. Right?
Yeah, that's what I showed. When you go r close to 0, you don't get a Kazner form, you get just...
Yeah, I know you don't get a Kazner form, but what I'm saying there is that at that point in the center and on the horizons, it does not look locally like Minkowski. So I'm not sure why there's any reason to say you can pass through it.
There's a part of the space-time which you can pass through it without feeling the orbifold singularity.
But the metric is it does not... We believe in GR when it locally looks like Minkowski space. But it doesn't locally look like Minkowski space. The sense in which it doesn't, who cares? But the moment you have that, I think making any claim that you could formally pass through it in some analytic solution, I don't know what that is.
This is the reason why this has been an issue with strong quantum censorship. Maybe you're saying, well, this is just a very,
I just said I don't believe in GR beyond that orbifold singularity or whatever.
Well, I mean, and the intuition is correct, because this is what we show formally now.
But
you literally get it into a curvature singularity, so you cannot cross.
No, but even if we don't have that, right? Like, if we didn't have that at the inner horizon, if the inner horizon just smooth, then it just locally looks like Minkowski space, and so it's just a GR solution, and it's completely ordinary.
In this case, like, I don't see how you get that solution, for example, by treating GR as an initial value problem in evolving folds. I agree it's a formal solution that has an overfold singularity, and you can formally extend geodesics through it, but I don't think there's any...
That's the claim that I make. You could formally extend the geodesics through it, but
like,
if you ask...
It doesn't look like Minkowski space, so why are we...
So Oracle 0 is like, it doesn't have one dimension, right? Just 2D sort of, right? Because one direction is going to 0. Is that right?
Yeah.
So it's not really a manifold. Is it even a manifold?
It's not a manifold.
It's not a manifold.
It's not a manifold.
It really doesn't look like
Just it doesn't look like...
a portion of
There's no sense that we can have a little box that crosses that horizon that locally just looks like Minkowski space-time. Like that, to me, is the reason you need new physics showing up at the inner horizon, right? Is that seemingly this is a solution where GR isn't obviously breaking down. The metric is not going like degenerate or anything crazy like that.
I agree with that
Yeah.
intuition. Like, there was already something weird going on with this inner horizon, so it's not clear that you should really trust anything beyond it, and that intuition turns out to be correct. But technically, if you're a mathematical GR person, you would still talk about observers crossing this.
I'm not sure you would.
But this is the definition of the surface.
GR is about manifolds with metrics on them.
Yeah.
Okay, let me just maybe send you some references where they actually discuss this in math GR terms, properly defined, like K, Rajikovsky, and Wald wrote some papers on the quasi-regularity of such surfaces, and they're quasi-regular for a reason. There's still some sense in which observers can cross this surface, even though it's very weird almost everywhere. And as long as there's even one that can cross, that's already a problem, even though most of it might be impossible. Sorry, I don't know. Sorry. I will send you the reference, and it will be on.
Okay, so let's thank Marija again.